Record. All right, so this is I think I started this lecture last class, so this is a continuation of my lecture on unconstrained optimization with more than one choice variable. I think as a review, I gave you these four examples of things of why, in particular in economics, we care about optimizing when there's more than one choice variable, more than one thing is being chosen. In particular, this allows us to speak about trade-offs. Economics is probably not a valuable science at all unless we start thinking about trade-offs and why do you do what you do? It's because there's scarcity. I want a certain amount of this, but other amounts of this, and the level of consumption or leisure or food or shelter or whatever it is I'm choosing between. You need to talk about that in terms of trade-offs, and in order to talk about that, you probably need more than one choice variable. Okay, and I think we are on our ways to talking about that. And I showed you what structure looks like for two choice variables. It'll always pretty much look like this if it's unconstrained. Unconstrained means see how x and y could be any number in the real numbers. There's no limit. By the way, what's the most normal constraint? It's the budget constraint. A budget constraint is something that actually would limit what you could choose for x and y. It's very natural to say, well, you only have so much money, you can't buy whatever you want, you're constrained by your budget. And we'll talk about that later. But for now, let's just learn the basics of this, problems that look like this, or it could be min, could be max or min. And I believe I gave this to you before. The first order condition are that not the derivatives, but the partial derivatives of this objective function should be equal to 0, remember? So the partial derivatives of whatever the objective function is should be equal to 0 with respect to each choice variable. Those are called the first order conditions. If you're doing a maximization problem, then the second order condition is that the second derivative is negative. At least, the second order partial derivatives here is negative, and the determinant of the Hessian should be positive. Remember, that is what we would say for maximization problems. Now, switching to minimization problems, the only thing that changed, the determinant part doesn't change. So this condition here doesn't change. That's, by the way, what I have written here on the bottom is a way to write out the fact that the determinant of the Hessian matrix is positive when it's a 2 by 2 matrix. That's what this bottom part is here, the second part here at the bottom. So the only difference between a min and a max is that for a minimum, this second order partial derivative should be positive at this point x star y star. Hopefully this is a clear what I mean here, at. When I say at, when you see at written in a textbook or something, it means if I were to plug in x equals x star and y equals y star, then the second order partial derivative is positive. That's what this word at means. Okay, so that's it. That's the first order condition, second order condition for max, second order condition for min. Oh, by the way, I already did this. I'm sorry, I'm reviewing so much, but the second order conditions are more complicated because it's three-dimensional. And I showed you, remember I showed you like what a saddle point would look like. If you could rotate it, it would look like, sometimes it looks concave up or convex, and sometimes it looks concave down or concave. And therefore, you need a little bit more complicated second order conditions just to establish whether a point is a local min or a local max. Okay. Did we do this one? Did we do the quadratic function? I think we started.
I know you gave it to us to work on, and I know we started on it. I don't remember if
we started, but we didn't finish it.
I don't remember if we finished it or not.
Do you guys want to see it again? I have to say, like, this is probably the type of question I'll give you on the quiz. So, whether or not we've done it already, it's probably a good idea to do stuff like this again, and just to reinforce your knowledge and comfortable level of comfort with these sorts of problems, so that when the quiz does happen, you'll be the most prepared you can be. So let's solve this problem. I'm sorry, I'm going to use annotate. I do not have a...
Professor?
Yes.
Sorry, I came in a little bit late. Did you say the quiz is next class?
It is. The quiz will be on Thursday. So if you look at the syllabus, I've said
Oh, it's
exactly
on there?
what all the quizzes are, and I'm unless something extreme happens, I'm going to stick to the dates on those syllabus.
Okay, sounds good. Thank you.
Sure. I'm only telling you about the syllabus in case, for some reason in the future, you also forget when the quizzes are. There's only 5 quizzes and their dates have been predetermined. And I think it's April 8th is the next. I don't know what today is. Today's the 6th. Right?
Yeah, today's the
My
6th.
phone to tell me what day it is. Yeah. So I think it said April 8th on the quiz, which is this Thursday for quiz 4. And what will be on quiz 4, I think it's mostly going to be this, how to solve a maximization or minimization problem. I'm not going to tell you which one it is, but there will definitely be more than one choice variable. There could be 3. Let me think. If it's an in-class quiz, I probably won't give you 3. I probably would rather just give you 2. I don't want to commit to it, but I think the best way for me to give you an in-class quiz over this material would be an optimization problem with exactly 2 choice variables. So that's kind of what I'm planning on giving you. And this is a very simple one. I think maybe I'll give you one a little bit more complicated than this on the quiz, but maybe not. We'll see. My goal isn't to trick you, it's just to give you an incentive to learn it and then demonstrate that knowledge back to me. That's how college works. I'm sure you know that by now. Okay, so that's the first thing I do here is I sometimes use capital F for FOC. FOC1 is going to be what? Would somebody be willing to tell me what FOC1 is? When I say that, I mean the first order condition with respect to the first choice variable, which happens to be X in this case. What would it be?
Do you want the definition of FOC?
Oh no, I want the
Or
actual
just the
equation
answer?
for FOC1. Yeah.
I got negative 4x plus 2y plus 5 equals 0.
Negative 4x, I agree with. Plus 2y, I agree with. Plus 5 equals 0, I agree. Everyone agree with Jordan? I think he got it right. Okay, perfect. And then how about FOC2? By the way, does anybody have any questions of where that comes from? It's just the partial derivative of the objective function with respect to x equals 0. That's where it comes from, and it is correct. So maybe FOC2 won't be so hard. It's just the partial derivative. But now with respect to y, and that is negative 6y, correct? Plus 2x equals 0. Thank you. That was, well, no one gave that to me, but assuming you could have got that. Well, so the question now is, what do we do? The answer is solve the system of equations. It's like one of the first things we did in this class is, how do I solve a system of equations? Sometimes I call them a model, like solve a model. Well, there's 2 unknowns and 2 equations. You can solve that. Use substitution if you like. Let's move the 6y over here and divide by 2. I'll do a little arrow here. The arrow is like an implication. It's not equality. I'm not saying this equation equals this equation. I'm saying this equation implies that if I move the y over and divide by 3, I get x equals 3y, correct? See how I got that? X equals 3y. Now I want to plug that in for x here. Is that right? I think it's right. I will get negative 4 times x, which is actually negative 4 times 3y, which is actually, so maybe the implication now is up here. You don't have to draw arrows like this. I'm just trying to do this to show you where I'm getting where I'm getting this stuff. If I plug 3y into here, what do I get? Negative 12y, correct? I should be forcing you guys to do this. I could make you go into little breakout rooms and do it yourself and then make it a contest to see who can get the most right. Okay. This is what I get by plugging in x equals 3y into that first order condition. I think I can solve this by saying these 2 terms combine to be negative 10y. If I bring that over to the other side, I get 5 equals 10y. And if I divide by 10 from both sides, I get y equals 1/2. You guys agree with me? Have I made any errors to determine? By the way, I'm not just going to say y equals 1/2. I'm going to add a little star there. What does the star mean? It means it's like a critical point. It's a stationary point or a critical point or a solution to this system of equations. That's why it has earned a star. Okay, well, what about x star? X star should just be equal to 3 times y, or 3 times y star, which is, I think, 3/2, isn't it? So what do we have? We have a potential solution. I'm not going to say it's a solution. I'm going to say it's a potential solution to this problem. Hopefully on the quiz, I think on the quiz, I'll probably lead you through the steps. I mean, you'll have to do each step yourself, but like I'll say what I want you. I want you to find the first order conditions, solve the system of first order conditions. That's how you get your x star and your y star. And rather than you concluding, okay, that's it, we're done, we have the answer, I'll probably lead you to say, okay, now check the second order conditions or something like that. And you have to know what the second order conditions are. So let's think about that. I'm not going to even write SOC, or should I? No, I usually don't, but maybe in this case it makes sense to. Second order conditions is that fxx is, okay, you tell me, positive or negative? So I'll give this a little right here. Fxx should be positive or negative?
Negative.
Thank you. It's because we're doing a max problem that it's negative. If it were min, it would be positive, but it's a max. Okay, so what is fxx? I actually just want to take the derivative of this. So notice the left-hand side of this first order condition is exactly equal to the partial derivative of f. I'm calling it f now. I don't think I used the lowercase f anywhere else besides here, but now that I've used it, let's call this function f. What I've written here on the left side of this equation is fx. That is f partial derivative with respect to x. So if I just take the derivative of that again with respect to x, I'll get this, and it is -4, simply. So even this term at x star, y star, please don't be confused by the fact that a few minutes ago, I made a big deal about it's at x star, y star. And you might say, well, it's -4. How do I evaluate that at x star and y star? The answer is it's already evaluated at x star and y star. There's no x or y in there. Therefore, you just leave it as -4 and check to see, is -4 less than 0? Of course it is. So that first part of the SOC is good. Now we want the second part of the SOC, which is determinant of Hessian should be positive or negative.
Positive.
Thank you. Who said that? Can't tell. It's Amina, right?
Yeah.
Thanks, Amina. Det H should be positive. Okay, let's calculate det H. Do I need to write it out? Do I need to write out H? Would someone like me to write out H? Maybe we should. You know what? It should be easy to write out. That's the good news. Do I have room on my screen to write it somewhere? Over here? I could write it all the way over here. You guys think H? That's a terrible H equals. I've already got fxx. The upper left entry should be fxx, which is -4. I'm sorry, this is going to be right on the edge of the screen. How about fxy? That will be, somebody tell me, what's fxy?
2.
Thank you, it is 2. Same thing for fyx, they have to be the same. Fyy, I think we can look in here and see it's -6. So I want to just verify that the determinant of that matrix is positive. the determinant of that matrix is -4 times -6, which is positive 24, minus 2 times 2, which is 4, which is 20, right? 24 minus 4, I think it's 20, which is positive, which earns another check, which means we have the answer. This collection of choice variables, x star and y star, is not just a potential solution, it is the solution, or at least, let's think about that. Okay, how much have I talked about the difference between a local max and a global max? Not too much, right? What I would love is for you to use a little bit of intuition here, rather than a rule. And it's not that there aren't rules. Of course, there are rules to tell you, is this a local max or a global max, or both? Obviously, if something's a global max, it's also a local max. So is it just a local max, or is it also a global max? What are some ways you could tell this? Gosh, I'm not even sure if I'm going to make this more explicit later. Well, I don't know. Does anyone have any thoughts on how you could use some sort of an intuition to know, in this case, what I've highlighted in red isn't the answer is it's a global max, meaning that there's no other way you could put in an x or a y and get a value that would be higher than this, the value you get at x equals 3/2 and y equals 1/2. But how do you know? Does anybody have any sort of intuition as to why that's the case? So, you know, so by virtue of these two checks, that means, I'll continue with my arrows. That means we know this is a local. Local just means in a neighborhood of these points. It is a local max. How do I know it's a global max? Well, so I'm not quite remembering what I normally say to the undergraduate level of this class, but if you take a master's level, it's called Econ 614, which also is a math for economists. I would have you sort of prove this a little more rigorously. I would say, okay, prove that it's a global max. One way you can do it is to say the function f is concave everywhere. If the function f is always concave, then anytime you find a local max, it must also be a global max. And this function, you know what, I think that little bit is probably enough for you to answer questions in this class about it. Like, let's not worry about the more complicated cases. But if you ever wanted to be sure that the local max is indeed a global max, one way to do it, by the way, there's not just one way to do it, there are many ways to do it, but here I'll just give you one way. I'll give you one way. And that is, if the Hessian matrix is sufficient to convince you that it's everywhere, that these conditions here are met not just at x star y star, but everywhere, that means the function f is concave everywhere. And that means, let me say, this implies f is concave. Not just concave at a point, but concave everywhere. And that implies, I'll put down here, f concave plus local max implies, this arrow is the implication arrow. I'm sorry if this is a little hard to follow, but it implies global max. Okay, so on a quiz, I don't think I'll be asking you to sort of prove. I think maybe I'll ask a little bit of intuition about this. Like, can you say, do you think this is not just a local maximum, but a global maximum? And if I ask something like that, your answer should be, well, if the function is concave, that's kind of the only way I'm really telling you how to always know. Then in fact, this local maximum is a global maximum. And of course, right now, if I didn't put any sort of restriction on x and y could have been anything. So in order to use this logic, you would have to say f has to be concave everywhere for every x and every y. But once again, if in the future you weren't allowing x and y to be anything, but they had to be selected from some restricted choice set, let's say, right? Just a smaller set of x and y are possible to choose. Then, of course, you don't have to say f is concave everywhere. You just have to say it's concave in that choice set. And once again, there are more complicated rules. For example, there's something called quasi-concave. It means it's not quite concave, it's quasi-concave. That's good enough in a lot of cases. That's beyond the scope of this class. Yeah. If you feel like you like economics and you want to get a master's in economics, I encourage it. That sounds great. I hope you guys are encouraged to go on and do that sort of stuff. In a more theoretical and precise exploration of this mathematical concept, you will learn a little bit more, a deeper connection here between how can we say for sure that we found the solution to this problem? And that is, how can we say for sure this is a global max, not a local? And you will learn about things like not just what makes a function concave, but what makes it quasi-concave. But let's do that later, or not later when I see you in the master's program. Okay. For this class, the only thing I might ask you about is this one here, where if the Hessian matrix is such that the function is always concave, then it's not just the local max, it's a global max. Okay. Did that make sense? This whole discussion about a global maximum, but like I just want to let me just draw like a function. It's really easy for me to make this point in two dimensions, right? You have a line. Am I sharing the right thing? Hopefully I'm sharing the right thing. Yeah, I'm sharing the whiteboard. Here's a function which has a local max there. Oh, but wait, it has another local max there. Sorry, another local max, and this right? This is a function where x1 is a local max, x2 is also a local max, but only x2 is the global maximum of this function f. This is the function f of x. And you can kind of see where the problem is. Like if you're just focusing on this x1 and you're like trying to convince yourself whether or not it's the actual maximum value for this function f, in a neighborhood, you would look at it and say, oh yeah, it's fine in this neighborhood. But something, and the function is concave in a neighborhood of f. It looks like, concave down. It's a hill shape, not a bowl shape. It's a hill shape. Okay, so you think, okay, we're good. The problem is somewhere like right around here. I don't know, but like right here where I've made this red squiggle, it seems like the function stops being concave, starts being convex. And in fact, it's that fact. It's the fact that f looks like it's now changing from a concave function to a convex function. That's the whole issue that even allows x2 to be the true global max, right? So the only reason you have something wrong about x1 is that you have this area here where there's some convexity to the function at a distance, even though it's at a distance from the point x1, it still matters. You know, it's not just a local issue, like what's happening locally. It's like, wait a second, over here, it starts to be convex, and that leads to this other issue of x1 is actually incorrect. If you tried to maximize f over all real numbers, and your answer was x1, you would simply be incorrect because the true answer is x2. Okay, so in this class, I won't ask you to prove, at least in general, I won't ask you to prove that your solution is the true global maximum of the function that you're supposed to maximize. But I might ask you about this sort of weak concept that says, well, if it happens to be concave everywhere, then you're lucky. You happen to be able to prove it, you know? I don't want you to think that it's necessary for a function to be everywhere concave for, you know, x1 to be a global maximum. That's not true. Oh, so what I mean by that, like if instead of, you know, it could have some point where yes, it becomes convex, but you know, it's like this, and all of this convexity over here doesn't affect the fact that x1 is still the global max. It doesn't work that way. It only works the opposite way, which is if f is concave, then a local max is a global max. And so similarly, it goes the other way too, which is if you're doing a minimum, if you're looking for a minimum, the axes are going to be green. Whoops. You're looking for a minimum. Oops, I meant to draw curly lines. And you know, you have sort of like this going on here. You think this is a local minimum because it's convex. Oh wait, it's not, because there's another minimum over here, right? So the same reason, this, which is a local min, is actually a global min if f is convex everywhere. If f is convex everywhere, typing words with a mouse is unpleasant. F is x everywhere. That implies that this local min is also a global min. I don't know why I'm writing this all with my mouse. Okay, so this is the opposite conjecture. I think that's it. I think that's all I'd like you to know is if f is concave everywhere, then a local max is also a global max. That's one statement I'd like you to know. The other statement I'd like you to know is the one I've written here. If f is convex everywhere, then any local min is also a global min. And even though I've drawn this in 2 dimensions here, where like this is x and this is, you know, y, which is if y equals f of x, I want you to be able to think of that in more than just 1 dimension. Think of it in 2 dimensions, 3 dimensions, 4 dimensions. If you have 3 choice variables plus a 4th variable, which is the output of the function, that's 4 dimensions. Nobody's brain is good enough to think 4-dimensionally visually. We're just not equipped for that. But you can still use these mathematical concepts that I've given you. Those apply regardless of the number of dimensions. Okay? Let's go back to what I was doing here. Okay. So let's see the answer to this problem, because we've done it. Those are the first order conditions. Substitution tells us that y equals 1/2 and x equals 3/2. So that's exactly what we thought would happen, correct? Same answer as we did ourselves. But now let's think about the second order conditions of this problem, which we did. Remember, f(x(x) is the second order partial derivative with respect to x is -4. That's negative, which is good. The determinant of the Hessian matrix is 20, which is positive, which is good. Therefore, 3 halves and 1/2 is a unique local maximum. Oh, by the way, you okay with this word unique? Unique just means it's the only one, right? It's the only local maximum. It's so bizarre though, because there could still be another point that's bigger than this, even if it's a unique local maximum. So you actually have to go further than that and say, could there be a larger value of f somewhere else? And the answer is no, because f is concave, because of that reason I gave you with my graphs. So I think this is it. This is the answer. You guys understand how you got that? 3 halves, 1/2, and then how you even got this extra logic that says, yes, it's a maximum, and there can't be any other larger value of f's anywhere else. Could you do something like that on a quiz on Thursday if I asked you? Good. Let's see a little bit harder of example, because I could give you a little bit of a harder example. So here's a logarithmic function. Don't be afraid of logs. Logs are just functions too. Oh, by the way, now I'm restricting here. So even though it's not constrained in a like x and y are both similarly constrained, they're just restricted to be non-negative in this example. I don't want any negative numbers in my log. It just causes weird things to happen. So the weird thing is that it's not defined for negative numbers. Okay, let's do this problem. Someone want to tell me what to do? What's the first thing I should do? Pretend like this is the question on a quiz and you're like, oh crap, what do I do? I'm stuck. Help me, what do I do?
The first order condition.
What are they? Perfect. Who's saying that? Sounds like Kai.
Yeah.
Thank you, Kai. Thanks, Kai. What is the first order condition? I'll call it FOC 1 and 2. What's FOC 1? Parentheses, or not parentheses, but colon, saying what I'm about to write is the first order condition for x. What is it?
Just 1 over x plus y plus 1.
Very good.
Minus 2x.
Minus 2x. Almost done, almost perfect. That itself is not the first order condition.
Equals 0.
Equals 0. You got to have the equals 0 because otherwise you're telling me the partial derivative with respect to x, but you're not telling me the first order condition. But that is good. Thank you. FOC 2, what would you get there? I won't make you say it because it's so similar. Kai got the first one. I bet she could get the second one too, no sweat. The only difference is instead of negative 2x here, it's negative 4y, correct? There's a neat little trick here that it doesn't, you can get the right answer many ways from this problem. But does someone want to look at this and say, what's the easiest way to solve this? This is an algebra problem now. I have, well, you tell me, what's the next thing I should do? It's a maximization problem. I'm looking for the x and the y that maximize this function. I'm looking for the x and the y that will maximize that function. How do I find it?
Find x from the second first order condition.
You mean find it, like solve for x in this?
Yeah. So
you like move the 4y over, multiply everything by x plus 4y. Yeah, you could do that. You could do that. And it's good that you selected this one to solve for x because the x only appears in this one place. So actually, you're right, Kai. Do you want to do that, or do you want to see a way that I think I would think of that is maybe a little shorter?
Yeah.
What if you move the 2x to this side and you move the 4y to this side? Don't you notice that then these two equations will be the same, the one on the top and the bottom? You could essentially subtract the bottom equation from the top, something like that. You get what I'm saying? Like let's do this. Equals 2x equals 4y. And now I'm just going to erase this. And now I'm going to just subtract let's subtract the bottom equation from the top, and you get 0 because the left hand side is 0 equals 2x minus 4y. In other words, add 4y to both sides and you get 2x equals 4y. Did I go too fast here? I'm sorry if I did. You guys see how I got this? 2x equals 4y. If anything, I can just look at this
Yeah,
side of the
yeah.
equation, 2x, this side 4y, and say, oh, those have to be equal because the left sides are equal. That means the right sides have to be equal, which means x equals 2y. That's nice. Am I done? No. But I have this, now I can substitute. This will just make it easier to substitute in what x is here. Plug in x equals 2y here. What do I get? I'm doing an arrow now, not an equal sign. Arrow, instead of x, I'll put 2y there that says 1 over 2y plus 1. That's 1 over 3y plus 1. If I did it correctly. I think you'll see that this problem is no harder than the previous one. It's just the objective function happened to have a logarithm in it, and the other one didn't. But conceptually, it's exactly the same. Let's see what we got here. 1 over 3y plus 1 equals 4y. Unfortunately, I do think we'll have a quadratic equation here, which just happens when you have something in the denominator and something else in the linear term. Okay. What are we going to get? Let's multiply both sides by 3y plus 1. I get 1 equals 4y times 3y, which is 12y squared. Plus 1 times 4y is plus 4y. I'd sort of like to subtract 1 from both sides right now and make this a 0 on this side, which I'm allowed to do with my annotate feature of Zoom. Okay. Agreed? Let's pause a little bit. Does everyone see how I got here? And of course, I'm not going to force you to say yes or no, but I would like you to say no if you don't see how I got here. 0 equals 12y squared. Or if I made a mistake. If I made a mistake, tell me. I apologize if I did. But what do we got? 114. Nobody's saying no, that they don't. You can even chat it to me privately, and no one will know that you chatted it. I won't call you out. So feel free to privately chat me and say, I'm not sure how you got that 12y squared plus 4y minus 1 equals 0.
Did you just multiply the 3y plus 1 to the other side?
I did.
Okay.
Yeah, and then I subtracted 1 from both sides and I got this.
Okay.
I wanted it to be in this form so that I could use one of my favorite formulas, which is the quadratic formula. Why do I say favorite? I mean, favorite, I mean, it's something I might ask you to use because I don't think it's too much to ask that you can solve a quadratic equation. I won't make you solve a cubic. I won't make you solve a quartic equation. But a quadratic equation, yeah, I think I might ask you to solve that. And so here's another example where I'm asking you to solve this quadratic equation. I don't think you can solve this problem any other way. So what should I use? Y equals, let's go right into writing out the answer from the quadratic equation. If you remember, it's negative b plus or minus the square root of b squared minus 4ac over 2a. Okay, where this is a, this is b, and this is c. Let's just write it out. Negative b is negative 4 plus or minus. This is where you get the multiplicity of roots of a quadratic equation. You get 2 roots plus or minus the square root of b squared. B squared is 16 because 4 squared is 16 minus 4ac. Okay, a is 12, c is negative 1. So minus 4 times 12 times negative 1 is actually positive 4 times 12, which is positive 48. Correct? And then I'm going to now take this whole thing, and usually you just kind of like dividing by 2 here because 2a is often equal to 2, but it's not in this case. It's 12. 2 times 12 is 24. Yikes. Now we'll see. Was I nice enough to make this a perfect square? What do you think? 16 plus 48. What is that?
64.
64. 64 is a perfect square, isn't it? So this, by the way, you guys are okay with me doing the quadratic equation, right? You can see how I got this from that. Let me know if you're not, including private chats where I will not call you out. Okay, so this is 64. The square root of 64 is simply 8. And that means, do you mind if I save space here by just deleting that and putting in 8? Obviously, if you're watching a recording of this, you will have seen that and you can go back to it anytime you want. But those of you who are not, I wish the eraser maybe wouldn't erase the whole line, but there you go, it does sometimes. Oops, that's supposed to be a straight line. Let me just try again. A little bit better. I just want to put an equal sign here. You know, there's this mathematical, it's almost like mathematical snobbishness to say, oh, it can't be an equal sign because there's more than one. You can actually do this and make it an element of a set, right? I'm not going to be such a math snob to say, you know, what's implied here is y is an element of the set of two things. One is when it's positive and one is when it's negative. So it's like y, ignoring all this, is an element of what? And that is -4 plus 8 over 24. That's -4 plus 8 is +4, correct? 4 over 24, that simplifies to 1/6. Agreed? 1/6. This is the case when we use the positive here. And I'm using a comma to indicate this is a set with more than one element. It could either be 1/6 or -4 minus 8 is -12 over 24 is negative, I'm sorry, negative 12 over 24 is -1/2. So I have this as my potential solutions for y, right? How much time do I have? I'm going slow. Am I going slow or am I going fast? How's my pace? You like my pace?
I think it's fine.
Okay. I would like to find x also. Luckily, we have this nice relationship. X equals 2y. Let's go back to that. Say when. So now we need to start thinking of x and y pairs, because you can't just say what x could be and what y could be. They actually come together in pairs. So how would I like to write this? I would like to say x comma y is, you know, I don't know, you can do this. This is extra snobbishness, but the pair xy is either, let's take y equals 1/6 first. That would mean x is equal to twice that, which is 1/3. So that would be 1/3 comma 1/6. You don't have to write it this way. You could say, I mean, really what I'm looking for are these two potential answers for the first order condition. If y is -1/2, x is double that, which is -1. -1 comma -1/2. Okay, so this is a fancy way to write it, but you know.
Professor.
Did I make a mistake? Yeah, go ahead.
So why wouldn't you exclude -1/2?
Oh, thank you. Thank you, because I told you that in the problem, didn't I? I did. That's an excellent realization. Who said that? Jonathan? Tommy? I don't know. Somebody said that. I think it was Jonathan. Yes, very good. Okay, because y is restricted to be greater than 0. That means I can eliminate this one, and that'll actually save us some time. Yeah. Oh, that would have given a natural log, which is negative. That would have been a no-no. So yeah. Good catch. Good catch. I'm not even sure why was even allowed. Like, why wasn't there some sort of contradiction that occurred prior to this realization that, oh wait, like, y can't be positive? Like, shouldn't there should have been something that said, oh, can't even do it. Perhaps it was with the derivatives. Okay, well, regardless, it was an astute observation to say that y has to be positive, or no, sorry, at least not negative, which means this is our only potential solution. X equals 1/3 and y equals 1/6. We should now explore that because we haven't addressed the second order condition yet. You might be like, well, I'm sure it's a maximum. I don't need to check. And like if you're doing your own research and you don't really care about proving it to anybody but yourself, then okay, fine. But if you do want to prove it to somebody like the instructor of the class you're taking, it is a good idea to then do the second order conditions or a problem like this, a maximization problem. Okay, so I think I should delete all of my drawings, knowing that we got to this point, 1/3, 1/6, clear all drawings. And I think I have it on this next slide, that's exactly what I just did. Yep, so this is everything I just did. Getting to 1/3 and 1/6. If you want to see it written in much better handwriting than I had, here's what it looks like. And like I said, these slides are available on Blackboard for you to review at any time, including during the quiz if you want to. I can't stop you from doing that, and I don't really feel like stopping you. So if you're like, wait, what was the first order conditions again? You want to go back and look at the slides, that's fine. Okay, now let's think about the second order conditions. Okay, before we do that, let's look at it right from this page. So we have, I'm going to annotate again. We have this x equals, I think 1/3, and y equals 1/6. Now we want to, I guess it's a preposition at. This preposition at might actually mean something now, because we need to evaluate the second order conditions at this point, x equals 1/3, y equals 1/6. Okay? What are they? I should have left up the first order conditions, if no other reason that they had the partial derivatives. I have to write it again. X plus y plus 1 minus 2x. And f of y equals same thing, but minus. I'm writing this again, not because we need it, but because it'll help us to find the second order derivatives. Okay, just a nice visual aid for when we're doing this. What do we really want here? We want fxx and fxy and fyx and fyy. But let's start with fxx. These are the second order partial derivatives of this objective function. Okay, anybody want to help me out here? What would fxx be? Not the numerical value once you plug in 1/3 and 1/6, but just the formula here in terms of x and y. We want to take a stab at it? How do you take the derivative of a fraction? 1 over x plus y plus 1 with respect to x.
Would it just be negative times x plus y plus 1 to the -2? Or
Yeah, x plus y plus 1 to the -2. I'm going to write that as 1 over x plus y plus 1 squared. But that's, yeah, I think what you said was right. Does everyone agree with what, I think it was Jonathan who said that? I think he's right. I mean, you could write this as -1 times this to the -2. It's the same thing. And did you mention the -2?
yeah,
Oh, perfect. That's right. What should we do next? How about fyy? Fyy is pretty similar. It is, because this whole thing is raised to the -1 power, we need to reduce the exponent by 1. -1 becomes -2. We need to multiply it by -1 because that's the exponent. So it's now -1 if there was a chain rule term, we would add that too, but there isn't. It's simply this, -1 over x plus y. Is my writing even legible when I use my mouse? You can read it. Jordan's shaking his head yes. Okay. You're speaking for the whole class, Jordan, with your head nod. -4, I've just becomes -4. And then the only one that's left to do would be the mixed one, which is fxy. Luckily, we don't have to do fyx. It's always the same as fxy. And that's the derivative of this with respect to y, or the derivative of this with respect to x. Either one. Let's do this one. The derivative of this with respect to y, luckily this -2x is going to go away, but this part won't. It's kind of the same beast we had before, -1 over x plus y plus 1 quantity squared. This is how mathematicians say that when you're squaring something inside of a parentheses, you use the word quantity, like x plus y plus 1 quantity squared. That way, you know, it's not just the one that you're squaring, it's everything in the parentheses. Okay, good. Now, finally, we have to use the word at. We have to use the word at because we're not just evaluating these anywhere. I mean, that might be good to know. What's it like anywhere? Fine. But for now, we want to know what's happening at this point, 1/3 and 1/6. Let's go right to it. Let's go right to it and say, what is the Hessian at this point? I want to actually solve for fxx at this point, fxy at this point, fyx at this point, fyy at this point. What do? I plug in these numbers here. You see these numbers plugged into here. Is this too much math to do all at once? We got x is 1/3 plus y, which is 1/6 plus 1. What is 1/3 plus 1/6 plus 1? Actually, 1/3 plus 1/6 is 1/2, right? Because 1/3 is 2/6. 2/6 plus 1/6 is 3/6. 3/6 is 1/2. So that's 1/2 plus 1 is actually 3/2. That's what belongs here in the numerator, 3/2. In the parentheses. When I square it, 3/2 becomes 9/4. Because it's in the denominator, if I want to express the 9/4 as a proper fraction, it becomes 4/9. Instead of 1 over 9/4, it becomes simply 4/9. There's a negative in here, so it's -4/9 minus 2. I need a little paper and pencil here to write it out, but -4/9 minus 2, what is that? That's 2 is equal to 18/9. -4 minus -18 is -22/9. I think that's the answer. -22/9. Do you guys want to check me? I know there's a lot of this is just arithmetic right now. Use a calculator if you're not sure, right? Just plug it in with a calculator. I think the answer is -22/9 there. Although I did a lot of math in my head. What do you guys think? Am I right? Oh, did I do the -2? Yeah, I did. I did the -2. I just plugged
Yeah,
in. You got
I
the same
checked it.
answer? Somebody?
I used
Hi?
the calculator and
You also
I
got
that.
-22/9?
Yeah.
Great. I think it's right. All right. Well, one good thing is, you know, we calculated -4/9 for this part. It's going to be the same everywhere. This is still going to be -4/9 over here. -4. Oh, that's bad. And I actually don't like where I wrote it. All right. Here, that's better. -4/9. -4/9. And now I want fyy, which is this term -4/9 minus 4. 4 is actually equal to 36/9. So I have -4 minus 36 should be -40. You guys agree? I believe this is the value of our Hessian matrix evaluated at the point x equals 1/3, y equals 1/6. And this is sort of a critical addition that this problem has that the other problem didn't have. Example 1 didn't have you actually plugging these numbers into the Hessian matrix because the Hessian matrix was just a bunch of constants. Here, it's not constant. So what? You can still evaluate it as a number by plugging it in for the values of x and y. And unless I made a mistake, I think this is what the Hessian matrix should look like. Let me know if I made a mistake. I think it's right. So what are we doing now? We're trying to confirm that this is indeed the maximum by checking the second order conditions for maximization. Well, the first one is that this top left term is negative, which is, I'm going to make a green check. No, let's see this. No, this term here, fx, should be negative, and that's a good. We're go. Okay, now we need the determinant of the Hessian is positive. A lot of numbers going on here, but you know what? I can just tell. I can already tell that it's going to be positive. The reason I can tell is I could just ignore the 9s and and say what's 22 times 40 minus 4 times 4. I'm sure that 22 times 40 is bigger than 4 times 4. So whatever the determinant of the Hessian is, it has to be positive. You guys want to calculate it? If anybody's feeling generous, they could calculate exactly what the determinant of the Hessian is. But I'm sure it's positive. I guess my suggestion to you, maybe if you're doing this like as a problem, and you have the time, maybe actually calculate out what the determinant is, so you can show me, yes, I did check, it is positive. Has anybody got a calculator that has worked out what det H is? Something divided by 81.
Yeah, 864, I think.
8.54?
Or 864, maybe.
854?
64.
That seems high.
Yeah.
Did you not divide by 9? By 81, really? It's something like
96.
that. Like, it's maybe that's it. Maybe it's 854 over 81. Is that what it is?
864 over 81.
Okay.
I don't know. I think I messed up, but I know it's positive.
It's something like that. It has to be positive because this number and this number are both bigger than these cross partial numbers. So A times D is certainly bigger than B times C, of course. That's why the determinant is positive. It's something like 10.
Well, that and they're all negative, so if you multiply them together.
Well, so no, that's not quite right though. Like, let's say this was a 40 and this was a 41, then it would not work. Or let's say they were both 40s even. Let me undo this. I want to make this point because I think you're sort of right, Jordan, but you may have just made one logical error when you're realizing that actually when you're subtracting two negative things being multiplied together, that's the same as subtracting. That's like 3 negatives. So that could be like this matrix here with the 40s. This would not have a positive determinant because, yeah, sure, this would be a positive number, but you're also subtracting a bigger positive number, which would make it not, in fact, it would no longer be a maximum at this point because with a Hessian that looked like this, you would say, well, for this particular function, this point, which you thought was a maximum, actually isn't, because there's some direction you could go where the objective function gets even bigger. Therefore, it's not a maximum. But luckily for us, I'm only bringing this up just to address, I don't want you to have a misconception that says, well, if all the numbers are negative, then we're fine. That's not true. You actually do need to compare the numbers in some way. But we did, and Kai checked it with the calculator, and yes, it is positive. So let's tie this all together, this problem 2. I'm running out of time here. So example 2 shows us, even with a problem that has a logarithm in it, and not only does it have a log, but it also has quadratic terms. So this is a problem which sort of mixes logarithms and quadratic terms. We can use this method to find a solution, a potential solution for x and y, 1/3 and 1/6. We still shouldn't be convinced for sure that that's the actual solution, because it's finicky. You know, what's really going on is best captured by this Hessian matrix. But because the Hessian matrix satisfied both of these conditions, the top left term was negative and the determinant was positive, then we can be sure that this is indeed a local, not necessarily a global, but a local maximum of this function. What about global? You guys have any thoughts about this? Do you think this is always concave? Is there some way to look at the fxx, fyy, fxy, and what it would be all together to convince ourselves, actually, this function is always concave? Can you tell anything about the sign, S-I-G-N, sign of these derivatives?
If
want you
all
to-
of
I want-
them,
Who's
this
talking?
is just a guess, but like
Hi.
fxx, fyy, and fxy, if they're all negative, then it's concave.
So
everywhere.
just because fxx is negative and fyy is negative, and they will be, that doesn't mean the determinant of the Hessian will always be positive. What you actually need is that they will be bigger than fxy in absolute value. Sorry. It will be bigger in absolute value than fxy or fyx. And that actually we can tell. So this is like, I would think of this as sort of like a bonus, right? And a quiz or an exam. Like if you got this far with these green checks, I'm going to give you full credit on a problem like this to say, okay, you used the first order conditions, you solved the system of equations, you found a potential solution for x and y, and then you use the second order conditions to check off both conditions. The first one, that fxx is negative and that the determinant h is positive. You used both of those to confirm that this point is indeed a local maximum. I would sort of consider that as, I think that's pretty much good enough for this class. However, to go one step further, you'd say, now how can I be certain that it's a global maximum? You could sort of just try to use your intuition about, you know, this function looks like it's concave. This one looks like it's concave. This one also looks like concave. It's like 3 concave functions. Probably when you add them together, they're going to be all concave. Even that doesn't always work, I think. Wait a second. 2 concave functions added together, are they concave? Maybe that does work. Does anybody know this? Why am I blanking on this piece of mathematical knowledge? Actually, I think that is true. I'll check, but I think it's true that any two, you can, like this is the sum, if indeed all 3 of these are concave. Maybe this first term isn't always concave. Yeah, that's what's going on here. Sorry, so you can't use that, even if it is true, even if it is the case. But let's say you wanted this sort of bonus. If I asked the bonus, like, okay, now prove that it is not just a local maximum, but a global maximum of this function, you could try to use the fact that to check to see if f is concave. And I think you will find that f is concave in this case. When I say f, I mean the whole function. I'm not breaking it up into 3 like I was just for a brief minute there. I'm now thinking of it all together. Is it concave? I think the answer is yes. And one way I can see it is that this term fxy is always going to be smaller in absolute value than either fxx or fyy. And all 4 terms will always be negative. So the Hessian will always look like 4 negative numbers, but it's going to have this property that this, if it's a, b, c, d, this term here, b and c, will always be smaller in absolute value than either a or d. That means the determinant a times d will always be bigger than B times C. Therefore, AD minus BC will always be positive. Therefore, the function is concave. Therefore, that's a proof that this is a global max. Like I said, I think that's more of a bonus type of level of question, but maybe it made sense to you. Hopefully it did. Do you guys have any questions about this answer? I would like to clear my drawings if that's okay. I'm going to clear the drawings and advance on. So here are the second order conditions. Yeah, you can see here, when I calculated the determinant, I didn't actually calculate it. I just said 22/9 times 40/9 minus 4/9 squared is greater than 0. That's really easy to see, so I didn't even calculate it. So this point is, notice I put the word here, local max. And for the purposes of this problem, I think that would be okay for the full credit. Because the question is, well, what if there's something else that, what if the local max leads to some bizarre behavior far away? I'm sort of saying to you now that I'm not going to give you a problem that has this really bizarre behavior on it. It would require sort of a more complicated objective function, and it's unlikely that I would give you something like that on a quiz. I think we should stop here before I go on to problem example 3. We'll see if we want to talk about this example 3 next class. Oh, here's one with 3 choice variables. Ooh, fun. I won't give you one with 3 choice variables on the quiz. I'll give you one with 2 choice variables. I'm not telling you what objective function I'm going to use. It could be anything, but it will be an objective function that you should know how to differentiate. And once you find the derivatives, it should be something that you would know how to solve that system of equations. That's what I will say. You guys have any questions about this material? How do you feel about it? You feel confident? You think you're going to ace the quiz? Good. Confidence is good. Overconfidence is bad because it might lead you to not take it seriously, but confidence is good. I'm gonna stop recording. Anybody wants to say anything?